Hey guys, Mr. Brown here, and this presentation will cover the section 4.6 from the OpenStax text. In this section, we are going to take a look at VSEPR theory, which allows us or helps us to construct 3D molecules from the 2D representations that we've been drawing with Lewis dot diagrams. We know that we're representing 3D structures on 2D space, and so the VSEPR theory helps us to take that 2D structure we've been drawing and use some information we know about atoms and electrons and arrange them around a central atom in the correct shape. So on this slide we have a representation of what we will be talking about. This is the carbon tetrahydride molecule, which is more commonly known as methane, a carbon with 4 hydrogens bonded to it. And if we were to count our electrons and put the carbon in the central and draw a correct Lewis structure, we would arrive at the representation we see there on the left with the carbon and the 4 hydrogens bonded to it. However, a molecule of methane, an actual molecule of methane, is better represented by the model that you see there on the right, the 3D model. We see that the carbon atom is in the center, and then we have the hydrogen atoms arranged around that central atom in such a way that they are all as far apart away from each other as possible. And we call this arrangement in particular, this is called a tetrahedral shape because it represents, if you were to put lines on each of the hydrogens, you would form a tetrahedron. Before we go any further, we want to define two terms that we're going to use as we talk about these structures. The first one being bond angle, which defines the angle between two bonds to a common atom, and it's measured as circles R in degrees. And there's a representation down here with the COH2 molecule. We see that the central atom is the carbon atom, the C there in the middle. And then to that atom, there are 2 hydrogens bonded. And so if we measure the degree of separation between those 2 hydrogens, we would see that it's 118 degrees, and we would call that a 118 degree bond angle between those 2 atoms. The bond length is the distance between 2 nuclei of bonded atoms, and we see a representation down there between the carbon and oxygen. So the amount of space between those 2 nucleuses would be referred to as the bond length. And we often use angstroms or picometers for these measurements. It's very, 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 very small, obviously, and of course. Angstroms are equal to 1 times 10 to the negative 10th meters, and picometers are just a little bit bigger at 1 times 10 to the negative 9th meters. Now that we've got some of the introduction and definition stuff out of the way, let's talk about the valence shell electron pair repulsion theory, more commonly called VSEPR theory. This is going to help us to determine the geometry of electron pairs. Notice it says both bonding and non-bonding around the central atom. So we will look at pairs of electrons around that central atom that are both bonded to other atoms and any lone pairs of electrons on the central atom as well. VSEPR theory says that electron pairs will arrange to maximize the distance between themselves. So all this is saying is electrons, as we know, have that negative charge. Negative charges repel other negative charges, and so therefore where we have these regions of electrons, they don't want to be close together, and so they arrange themselves, as we just saw with the methane molecule, in ways that allow these bonds and lone pairs to be as far apart away from each other as possible. While this is a really good theory, it only accounts for electron interactions, and there are some other factors that may influence. So as with everything else, this is sort of a base level theory. It does a very good job of predicting the geometry of small molecules. But of course, if we got into larger molecules and if we wanted to be a little bit more exact, there are some other interactions that may need to be taken into account. But this is a very good theory for predicting the geometry of small molecules. So here on this slide, I do want to address one thing before we go any further into these structures. We will talk about two different geometries for each single molecule, and those are the electron geometries versus the molecular geometries. And I have an example for you here. The ammonia molecule with the formula NH3 would have a correct Lewis structure that shows 3 hydrogen atoms bonded to a nitrogen atom, but the nitrogen atom does have a lone pair of electrons with it also. And so the electron geometry, what we would call the electron geometry, will include the model that looks like this in this box right here. And what we notice is all 3 hydrogen atoms are bound to the nitrogen atom and the electron pair is shown. And this will be, we will call this tetrahedral electron geometry, and we'll go over what all the different shapes are in just a few more slides. But this would be considered tetrahedral electron geometry. However, we also will sometimes consider the molecular geometry, which is represented in this box right here. And we see that the molecular geometry accounts for the atoms that are bonded to our central atom, but it does not include the lone pair of electrons. So molecular geometry doesn't include the lone pairs attached to the central atom. You may notice, however, that the bonds are still in the same direction. Even though that lone pair is not shown, it's still there, and its effects are still felt, and therefore these hydrogen atoms are still pushed down a little bit. Now we would call this geometry trigonal pyramidal geometry without the electrons shown. So the electron geometry would be tetrahedral, while the molecular geometry is trigonal pyramidal. We will see those two different geometries described and asked for all types of molecules. Here on this slide, we see all of the different possibilities for the different shapes that we could see for most of our molecules that we will encounter in Chemistry 151 or any general chemistry course. And this gives you an overview of how to determine the different geometries, both electron geometry as well as molecular geometry, based on how many regions of electron dense areas and what types those areas are found around a central atom. And so in order to determine molecular geometry, like we see here, the first step is always drawing a correct Lewis structure. So you want to place your electrons in your bonds, make sure octets are satisfied, and make sure you have the right number of electrons. Once you feel pretty certain that you have the correct Lewis structure, you're going to do some observation about the structure you have drawn. First thing you're going to do is determine the number of electron dense areas around the central atom. Note that bonds, even if they're single, double, and triple, that only counts as one area of electron density. So they're going to kind of stay together, even a double bond and a triple bond. And you will determine how many of those electrons dense areas are lone pairs. If we remember back to that previous slide, we will do two different kinds of geometry, one that includes the lone pairs and one that doesn't, even though the electron lone pairs always influence the geometry. And then we see that those electron dense areas are arranged so that they are as far apart as possible. Bonds want to be away from each other. Bonds want to be from lone electron pairs, and lone electron pairs don't want to be next to each other either. So once you have those things determined, you can easily consult a chart like we see here on this slide and determine the geometries associated with that structure. If we only have two regions of electron density, then the electron pairs or the electron geometry must be linear, because the furthest away you can arrange something around that sphere is on opposite sides, so a line would move straight through them. And in that instance, we generally don't see lone pairs, and so that would give us a linear molecular geometry as well, because we would see one atom bonded to each side of the central atom. If we have three regions of electron density around the central atom, then the electron geometry is arranged as a trigonal planar, so it's three sections sticking in a plane, or sticking flat out in a plane from the central atom. If none of those lone pairs are, or if none of those electron density regions are lone pairs, then the molecule also has trigonal planar geometry. However, if one of those regions of electron density is a lone pair, we would call the molecule a bent molecule. Water is a good example of a bent molecule. So you can read this chart all the way through 4, 5, and 6 regions of electron density, and with different numbers of lone pairs as those areas of electron density, to see the different molecular shapes that you can come up with. On the next couple of slides, I'm going to show you a tool, an online tool that will help you both build these molecules and kind of determine the shape and geometry in 3D. Okay, so this is what I was referring to. This is called the PHET Molecular Shape Simulator, and if you are following along on this presentation online, I believe you should be able to click this link here and the simulator will pop up for you. However, if not, you can simply Google PHET Molecular Geometry Simulator or something like that. They have a bunch of simulations, a bunch of science simulations at this PHET website. It's done through the University of Colorado, I believe. It's very clean, no ads, no software or anything installed. So it's a really great website for science simulations. So you might have to dig through a few if you have to Google for it. Hopefully the link works. In any case, the way the molecular shape simulator works is they give you a central atom. The purple atom there that's kind of hard to see is always there, and you draw a correct Lewis structure, and then whatever the Lewis structure shows, you put around that central atom. So if you see 3 single bonds in a lone pair, you click 3 single bonds, you click on that single bonded atom right there 3 times, and you click a lone pair 1 time, and it will throw those bonds and lone pairs to the central atom there, and they will push themselves away from each other, just as these negative charges would repel. This computer simulation has these bonds and those lone pairs repelling away from each other as you add them. You have some options. You can turn on and off the lone pairs. It will even show you the bond angles if you turn that on, so how far apart, how many degrees apart each of these bonds or lone pairs are. And then down in the bottom you have check boxes for either showing or hiding both the molecular geometry and the electron geometry. I hope to have a video of some live demonstration of this soon, but on the next couple of slides I will show you the results of some of my workings with the PHET molecular simulator. All right, for our first example here, we're going to determine the Lewis structure as well as the electron and molecular geometry for CCl4, also known as carbon tetrachloride. So to do the Lewis structure, which is what we have to do first for carbon tetrachloride, we will count our valence electrons to begin with. So carbon has 4 valence electrons, and chlorines each have 7 valence electrons, and we see that there are 4 of them. So that's 28 valence electrons from the chlorines, and so that would be a total of 32 valence electrons to place around each of my atoms in the Lewis structure. So I will put the carbon in the center as it is the least electronegative, and I will bond each of the chlorines to it. Then I will complete octets with the electrons that I have left over. Since I have 32 electrons, if I put 8 around each of the chlorines, that should equal 32. Everybody has satisfied octets, and so therefore the Lewis structure for carbon tetrachloride looks like what we have drawn here. And then we have captures of us being able to build the molecule here with the PHET website. So we notice that the carbon has 4 single bonds and no lone pairs, and so if we use the PHET website to put 4 lone pairs around the central atom, we see that they push away from each other, and we have the molecular geometry and the tetrahedral geometry shown here. Now, since the central carbon in carbon tetrachloride does not have any lone pairs, the molecular geometry and the electron geometry match. And you can see that they are both tetrahedral. In this example, we are going to evaluate the Lewis structure and electron geometry of tellurium tetrafluoride. And if we want to draw a Lewis structure, the first thing we want to do is determine the total number of valence electrons we have to incorporate. And tellurium has 6 valence electrons, while fluorine each have 7 valence electrons. There are 4 of our fluorines for a total of 28. So we have 34 total electrons to work with. If we draw the structure, we would put tellurium in the middle as it's the least electronegative, and we would bond each of the 4 fluorines to it. And then we would place our electrons around each of the terminal atoms to fill their octets. And if we went and counted these electrons, everybody has satisfied octets. However, we've only used 32 of the 34 electrons. So we would have to find a home for those last 2. They can't just be tossed away. Luckily, tellurium is a rather large atom. You can tell due to its position on the periodic table. It's really pretty far down. It has some d orbitals in which it can plug some electrons in, and so it can go as we say, hypervalent and have a few more than 8 valence electrons. So we will put those last 2 on the tellurium. With that done, we have our structure complete. This is the accepted Lewis structure for tellurium tetrafluoride. And to determine the geometry, we would use the PHET tool or one of the charts. And I have another demonstration of the PHET tool here. We have the central atom placed for us, so we will put the 4 single bonds around the tellurium atom. It also needs a lone pair, and once we put the lone pair, we can see that the molecular geometry is what we call seesaw. And I turn the molecule here in just a minute so that you can kind of get, there it is, a visual of why we call it a seesaw, the old playground toy. The electron geometry is different now because we do have a lone pair, and so if you are factoring in the electron geometry of the lone pair, we call that trigonal bipyramidal, because you can imagine 2 trigonal pyramids extending from the central atom, with 2 of the terminal atoms being the tips of the pyramid. Here on this slide, we see the Lewis structure and molecular geometry, as well as the electron geometry for phosphorus trihydride. We can see that the phosphorus has 3 single bonds and a lone pair. And if we input this into our chart or our modeling system, we can see that the molecular geometries, the arrangement of just the atoms, is trigonal planar, while if we include the lone pair of electrons, we would refer to that as tetrahedral geometry. Here on this slide, we have an O3 molecule, which is commonly called ozone, which protects us from harmful UV radiation coming through our atmosphere. We find a lot of this compound up there that helps to mitigate some of that UV radiation that comes through. We can see that the Lewis structure consists of a central oxygen atom that has a double bond and a single bond to it, as well as a lone pair of electrons. And if we arrange this molecule into our modeler, we see that the molecular geometry, the arrangement of just the 3 oxygen atoms, is called a bent geometry, while if the lone pair on the central oxygen is included, we would refer to that as trigonal planar geometry, meaning just kind of a triangle on one plane. Here we have the sulfate ion, and we can see the Lewis structure drawn here, and the tetrahedral geometry that results from this arrangement. This is the carbonate ion and its structure. We can see the Lewis structure down here with the carbon that has 2 single bonds and a double bond, no lone pairs. And if we arrange that in our modeler, we can see that we would refer to this as trigonal planar geometry. Here we have the PF6- ion, and we can see that the arrangement of the PF6- ion would have a phosphorus central atom with 6 fluorines bonded to it by single bonds, and we can do that because phosphorus is one of these larger molecules that's hypervalent and can accommodate a few more than 8 valence electrons. In this case, he's accommodating a share of 12 valency or bonding electrons. In any case, we treat phosphorus as the central atom. We put our 6 single bonds onto it with no lone pairs, and we can see that this would be referred to as an octahedral arrangement, both electron and molecular. It kind of looks like the old toy jacks, resembles that shape. Here, finally, on this slide, we have the ClF3 molecule. We see if we draw the correct structure for ClF3, we have a central chlorine atom with 3 singly bonded fluorine atoms, as well as 2 lone pairs of electrons. And so if we use our modeling system, we would see, or we would need to put 3 single bonds onto the central atom along with 2 lone pairs, and we can see that the molecular geometry, the arrangement of the atoms, would result in what is known as a T-shaped geometry, and the electron geometry is going to be trigonal bipyramidal. Now that we have seen how some of these molecules appear in 3D space, we're going to address something known as polarity. And what polarity describes is the amount of sharing that actually goes on within a molecule. Sometimes when we say a covalent bond shares electrons in a bond, that doesn't mean that those electrons are always shared equally. Sometimes one atom may get a larger share or have more share of that electrons than other atoms involved in a bond. When that is the case, we call our bond polar. And there's an example of it. You can see the polar bond example right here in this example. So in a regular covalent bond, a nonpolar covalent bond, we would see a completely equal sharing of electrons, and that usually happens when we have 2 of the same atom bonded together, or 2 atoms that are really close in electronegativity. But when you have two atoms sharing a covalent bond in which there's a big difference in electronegativity, you will get a polar covalent bond in which the bonding electrons are shared with more of one atom than the other. On this slide, we show how the direction of charge and unequal sharing of electrons is symbolized very often. So you will see these vector arrows that lie above or below bonds in certain chemical representations. Vectors, just so we're clear before we go any further, vectors are a mathematical instrument that are used to indicate direction and magnitude, and they can be used for direction and magnitude of speed or of force or of energy. In this case, it is separation of electric charge. So how far and how much the positive and negative pieces of these bonds are separated. The positive part of the molecule will have the little line and the tail of the arrow, and the arrow will be pointing toward the more electronegative element, because the more electronegative element, for this in this case is carbon and in this case is fluorine, will pull more of those electrons. They will have a greater share of the electron density. And the length of the arrow gives you some indication about how strong this pull is. And so in this case, we could comparatively say that carbon doesn't pull or doesn't have as much of the electron share as an atom like fluorine when it bonds, due to the length of that vector. One of the useful thing about vector representations is that they can be summed together. And so when we take into account an overall molecule, we take into account all of the dipole moments that are present to determine whether or not the molecule itself is polar. We see an example here with carbon dioxide. Carbon dioxide does contain some polar bonds between the carbons and each oxygen. So carbon dioxide, or these carbon-oxygen bonds, are very much in favor of the oxygens. They get more of a pull of the electrons. So while these bonds are polar, however, the molecule itself is overall nonpolar. And the reason for that is each of these vectors, which are equal in magnitude but opposite in direction, would actually cancel each other out. Because they both pull in opposite directions with the same amount of force, then overall the electron density ends up spread rather evenly around the molecule. Now take into account something like water. We see with water we have two bonds that are being pulled, or the oxygen atom is pulling electrons from two different directions toward itself. The oxygen pulls with the same magnitude in both directions, in both cases. However, those magnitudes or those vectors are not exactly opposite of one another. So when they add each other together, there won't be this canceling effect. There will be a little bit of an additive effect, which means that overall, the overall dipole moment has a negative region of space near the oxygen and positive regions of space down here. So that means water is a very polar molecule because its overall dipole moment is not canceled out. On this slide, we have an example of a molecule that would be polar because of unequal individual dipole moments. So we can see in the spinning molecule here that we have a carbon-oxygen bond and a carbon-sulfur bond. Both of these bonds are polar. The sulfur pulls on the electrons more than carbon does because it has higher electronegativity, as well as the oxygen pulls on the electrons harder than carbon because of the higher electronegativity. In fact, oxygen pulls a good deal harder than sulfur does. And so if you evaluate the overall polarity of this molecule, we would say that this is a polar molecule. because some of the electron density will be pulled over to the oxygen here because the sulfur electronegativity is not quite enough to cancel it out. So in this molecule, we would have a little bit of positive region here and some negative region over here. Overall, this would be a polar molecule. This is an example of a nonpolar molecule that has a lot of polar bonds. Each of these carbon and chlorine bonds is very polar. The chlorine is much more highly electronegative than the carbon is, and so they all pull with, they all share an unequal amount of those electrons. However, each of these is very symmetrical. Each of these is pulling on each point of those tetrahedrons in an equal amount because they are all carbon-chlorine bonds. And so therefore, overall, each of these pulls or each of these unequal shares would be canceled out, resulting in a non-polar molecule. And so I like to include this little discussion with my students here. Don't let this discussion of vectors and all that hide the big idea. Here's the big ideas when it comes to molecules and polarity. Molecules can have polar bonds and not necessarily be overall polar. Molecules are polar if they have those polar bonds, but they are not balanced out by other polar bonds. So in essence, molecules are nonpolar if they have no polar bonds or they have polar bonds that are canceled out by symmetricity, equal and opposite bonds. To consider a molecule polar, it has to have an electronegative atom, something that's going to pull on electrons unequally, something like oxygen, fluorine, chlorine, bromine, iodine, nitrogen, as well as be asymmetric. The only way that you can have that not balanced out is have an asymmetric molecule. So when you're looking to determine if something is polar or not, first look and see if there's any polar bonds, if there's any things like oxygen, fluorine, chlorine, bromine, and then make sure that it's not balanced out on the other side. If that's the case, then you have a polar molecule. I'd like to end this discussion with a little bit about why we care about polarity. Just a few notes. In an electric field, polar compounds, we can get them to line up, which becomes very nice for different analysis and separation techniques. Also, polar solvents dissolve polar molecules, and nonpolar solvents dissolve nonpolar molecules. It's a axiom in chemistry that we call like dissolves like. And that's useful for when you're trying to decide how to run a chemical reaction. It's also the explanation of why oil and water do not mix. If you've ever tried to mix oil and water, you can clearly see that one does not dissolve in the other. And the reason is we've shown water is a rather polar compound. Oils and fats and greases are not hardly at all. They are very nonpolar compounds, and so they do not mix and they do not dissolve in one another. So our question here is this a polar or a nonpolar molecule? We can see in this molecule that there would be one polar bond here because carbon and oxygen have differing electronegativities. So oxygen has a greater share of the electrons. It unequally shares its electrons with carbon. Because there are no other polar bonds, carbon and hydrogen is not a polar bond. It is a rather equally shared bond. Because there are no other polar bonds to cancel out this pull, this would be a polar molecule. This bond here, because it's symmetric, each is going to pull equally on those electrons. So this would be a canceled out pull, and this would be a non-polar molecule. In this example, we would see a polar bond here, a polar bond here, and a polar bond here. There is not a polar bond in this direction. If there was, it would be very, very tiny. The carbon and oxygen bond is rather equally shared. So we can see that each of these pulling in this direction would cancel each other out. However, we would be left with this polar bond here that would pull some of those electrons toward that fluorine, and this would be a polar molecule.